These are just some of the things that we use to prove stuff about ourselves. We use our face, fingerprints, emails, private keys, utility bills. All of these are attributes or stuff, but generally paper documents or paper-based stuff that is produced by somebody, handed to you, which you can then use as a credential of some kind to prove something about yourself. And we do these things to open bank accounts, buy goods, hire people, pay our taxes, everything necessary in order to go about our lives and establish we are who we say we are in the course of whatever it is we need to do. We're getting to a place where we can no longer trust anything that is presented to us that started in paper and ended up in scanned form or some digital mechanism where it's transferred from person A or party A to party B. Which means we need to take the information we capture and verify that with the original issuer. Now, the original issuers are in many cases government agencies, banks, regulators, people who are generally pretty tight with information. They don't like sharing anything. But what they don't realize is that they are actually the trust anchors of the digital economy. They hold the keys to the kingdom. They hold the information that allows us to prove things about people and businesses that are true. And the mechanisms that we need to be able to prove these things are these cryptographic protocols. So we have two parties involved in the zero-knowledge proof. We have a verifier, someone who seeks to verify something, prove something, and then the prover who has the authoritative information that wants to establish you have what you say you have, you know your password, you know your credit card, you know whatever it is. And the way we do this is by taking a piece of information that is secret, let's say it's a password, for want of a better word, and we obfuscate it with a randomly generated code, something that looks like a Rubik's Cube. So I have a randomly produced pattern of my Rubik's Cube, and I send this Rubik's Cube to you, and I say, apply this Rubik's Cube to your piece of information, please. Now, I know the secret piece of information already, and I've already applied this randomly generated code to the piece of information I have. And if I do that successfully, I should end up with a scenario where the information on one side matches exactly the information on the other side. So my two Rubik's Cubes should have exactly the same pattern for each, because I'm using the same code and the same secret. Now, I don't want to share one with the other, because that would be risky. And the way I prove that one matches the other is by testing permutations generated from one against the other. And the permutation might be, top row is all red on the front face. So I sent that permutation across to the other side and asked them, is the top row front face all red with you? And they go, yep. And I repeat that process 10, 20, 50, 100 times. And if I get a positive response back every single time to these randomly generated permutations, then the probability that these two things are the same rapidly approaches the perfect 100%. Never gets there, but it gets so close to 99.99999 forever, that close. So you can say, well, there's only one logical outcome here, that these two things are the same. Yet I've never shared the underlying secret. And that's why this is so useful. You can keep the information private. The 13th should be getting access to certain sites on the internet. Well, if I could prove that that person was under whatever age it is, or over whatever age it is, then I could reliably give them access to that service. You know, unfortunately, every self-respecting 13-year-old boy is going to tick the box to say, yep, I'm 18, I can get in. But the tick box is not the solution. So being able to prove something about yourself without disclosing anything else other than the fact you are under or over a certain age is extremely beneficial. And that's just one scenario. So it could be entitlement to a pension, for example. Are you over 65, under 65? Whatever those things are, you can prove these facts and use them for a useful purpose. This is coming next year in the European Union's digital identity wallet. We will all carry around credentials of one kind or another that we will have in our phones to be able to prove certain things about ourselves. But they are all based on strong identity, meaning I've established you are who you say you are, highly reliably, and that, I believe, has to be done with government data. And the only way governments are going to allow that to happen is through the use of these cryptographic protocols that secure the information. How multi-party computation works. Essentially, you can take a piece of information, break it up into pieces, store those pieces in a randomized network, and still process those pieces as if they were in one place, but they never come back together. They stay where they sit. So the analogy I use to try and bring this to life for people is, imagine I want to do a facial biometric authentication with you. Transpose your face into a jigsaw puzzle. Right, you are now the picture on the puzzle. What I'm going to do is I'm going to mask that puzzle, I'm going to paint it black so I can't see what's on it, and then I'm going to randomly take each piece of that puzzle and disperse them randomly to a big network. So the parties that get the pieces of the puzzle, they only see one piece and it's blacked out, so they don't know what they're holding. But they're going to be asked to do something every now and again in order to help solve a challenge or computation of some kind. So from a cybersecurity perspective, we've changed the nature of the risk, meaning no single party now has access to the entirety of the data. They only have access to a piece of the puzzle. The problem with multi-party computation means it's slow, which means we haven't been able to use it up to now because it can take minutes to hours to days for a computation to execute in some cases. And I'm going to show you a way that we've come up with making this much faster, which means it brings day-to-day scenarios into the realm of viability and usable, feasible applications. The analogy we use here is, what if you could use the internet storing this information? So any device that's on the internet potentially becomes available for storage of information. People struggle with this because they now think, well, that means I'm giving my stuff to some random stranger that's sitting on a phone or device somewhere and I have no control over it. Yeah, but they don't know what it is because they don't know where the rest of the puzzle is and they can't see what is actually on the piece of the puzzle that you gave them because it's masked, it's hidden. But the value from an entropy point of view of doing that is that you've now put pieces of information into a massive network where you don't know where they are. Nobody else knows where they are. So in order to reconstitute that information, you've got to find them, you've got to collect them, you've got to unmask them, and then you've got to process them. That's X by Y by Z by whatever. That is an absolutely massive number from an entropy point of view, which makes the security of the system really, really strong. And the analogy is, it's hiding in plain sight. Because you don't have to secure it. The randomness that you've inserted into the system is the security. But to run that little computation takes 40 minutes, which is ridiculous to do a simple authentication. The mathematics work, but it's just not feasible in the real world. So we need to solve this speed problem. And that's what we've done with messages computation. We figured out how to eliminate all these messages and do it in a way where all of the message exchanges now get condensed into the node that holds the original information. So all the processing now, instead of being internet transactions, become CPU level transactions. So instead of 100 milliseconds per transaction, we're now running gigahertz or fractions of a gigahertz. So really, really quickly. And that has implications in speed terms, anything from 1 million to 1 billion times faster, which takes my example again of my facial biometric authentication from 40 minutes down to less than a second, which means we can now use it. It was actually the combination of two cryptographic primitives, one-time masking and Shamir secret sharing, to create this new protocol, which we call messages computation. My analogy, it was when we had a knife, and we had another knife, and we put the two knives together and we created a scissors. And the scissors suddenly became really, really useful. It's as simple as that, where we're able to take the combination of two things, put them together and we solve a really, really difficult problem in terms of speed, but we've enabled something that we previously didn't have, which is the ability to collaborate securely and privately with others without having to burden ourselves with mountains of firewalls and routers and God knows what to keep our environment secure. So where could it be used? Secure data storage for the internet. Anywhere you want to secure and store something without running the risk it's going to be stolen. Truly decentralized storage. Making public blockchains private. So one of the things that we potentially looked at are how could you build bridging solutions between one blockchain and another using multi-party computation as the mechanism to execute authorization or authentication protocols between the different chains. This is going to be important when we get to CBDCs and stablecoins, and that seems to be the direction of travel at the moment.